So, okay, now I will explain what is uh, you know the concept of entropy and you know information gain using the same tree. Okay, let me just change the open a new notepad. Okay, let me construct the tree again. Okay, let me see what is the thing. Here you have 2 plus 3 equals to 5. Here you have 0 plus 2 equals to 2. 2 plus 0 equals to 2. 0 plus 1, 1. 2 plus 1, 3. Okay. All right. So this is your tree. Now we calculate the entropy. Okay. So the simple formula for entropy is minus of P plus log base 2 P plus minus of P minus log base 2 P minus. P plus is the probability of positive, or let's say 1. P minus is the probability of 0 or negative. So this is the formula for entropy. Okay. And when we are, let's write down the, uh, you know, formula for gain as well. So if you are trying to calculate gain of, I'll explain this later. Okay. So this is, sorry, is there a question? All right. Okay. So, okay, I will come to gain later when I will explain this formula. Maybe it will clear with an example. So let's calculate the things first, okay, and then we can see if there are any questions. Okay. So what is the entropy for this node? Okay, so for the first node, the root node. So this is let me write down here root node entropy equals to, so P plus. What is P plus here? So the positive, sorry, positive are 3. Okay. So 3 by 5. Okay. So the number of positives are 3. So this is the value, this is the number of samples where we have one value. This is the number of samples where we have zero value. So 3 by 5 times log 2 base, uh, log base 2 times 3 by 5 minus, this is the number of negatives. This is P minus log 2, 2 by 5. Okay. You use a calculator, calculate this value, this will come out to be 0.97. Okay, right? Similarly, you can calculate the entropy for all the other nodes. Okay, so this is a, I mean, you can calculate for this node. Okay, and using the same method, you do the calculation on your own, this will come out to be 0.92. You verify this result, okay, by doing the calculation. I'll just giving the answer. But can anybody tell me what will be the entropy for this, again, the leaf nodes, these three nodes? What is the entropy for these three nodes? I mean, if you are following the Gini impurity part, you can also answer this thing. I mean, again, see, These nodes are pure nodes. They don't have any impurity, as we saw while calculating the Gini impurity part. Okay. So what is entropy basically? So what is entropy basically? So entropy is the measure of disorderness of the system. So the more your system is disordered, more your system is in random, more it is chaotic, higher will be your entropy. you know so you have a glass, you break the glass shatters into pieces. I mean, there is more randomness in that system. You cannot get back your original glass by joining the pieces, right? So entropy of that glass, the broken glass, is more than your entropy of the uh, solid glass. Okay. So orderness and entropy are related. More is the order in the system, lower is the entropy. Higher is the randomness or chaos in the system, higher will be the entropy. Okay. So orderness means less entropy, chaos means more entropy. Simple. So here, if you see, these leaf nodes are predicting your population exactly. I mean, there are no impurity. I mean, they don't have. So here, if you see in this leaf node, you have this one. You have only one value which is positive. There are no negative values. Okay. So you either have only positive values in the leaf nodes or you have only negative values. So there are no, impurity, no disorderness. So the leaf node entropy would be zero. Okay. So again, similarly, as I explained, the decision tree, decides the cut based on whichever cut has the lowest entropy. Okay. And I think this is a question on, I mean, you have to calculate the entropy in one of the questions in assignment. And also, you have to calculate the gain, okay, information gain. Okay. So now using this example, we'll see what is information gain. Okay. And then I'll explain again the physical meaning of information gain. So let's say you want to calculate the information gain of uh, the tree given the age. Okay. So sorry. Yeah, age is the first cut. Okay? Age less than equals to 30.5. So you want to check what is the information that you are gaining by using this cut. Okay. So that is basically represented by information gain. So why will we use this cut? Because we are getting some additional information using this cut, right? That is why we are using this cut. Why otherwise why would we use this decision tree at all? Okay. So this information gain tells you what is the information that you are gaining by using this cut. So S is, let's say, the tree, and you are trying to get what is the information gain by using this age parameter or the first node. Okay. So this is calculated by, taking the entropy of the, without using this cut. So what is the entropy, without using this, you know, without using the first cut itself. So that is basically we calculated here, right? The root node entropy. Okay. So this is where you have, like, in the initial data, you have two zero samples and three one samples. And based on that, we calculate the entropy and it came out to be 0.97. And so we do 0.97. So this is basically this thing, entropy of the whole tree S. And then you subtract from here what will be the entropy, what will be the, yeah, kind of the weighted entropy if we use this cut. So this is the value of entropy that we will have without using this cut. And then from there, we are subtracting the entropy that we'll have if we use this cut. If we subtract these two, the remaining value that we have is basically the information that we are gaining by using that cut. Okay. Is it clear, or like is it becoming complex? It's clear, right? Oh, sorry. Okay. So again, so 0.97 we'll do, and then what we'll do is, we'll see. Okay, so we'll come to this node. So if you are using this cut, our tree is restricted to only this thing. Okay. So now we'll see this cut. In this cut, what is the uh, proportion of samples that we have in this cut? We have three samples. Okay. But what is the proportion? That is 3 by total, the 5, 3 by 5. Okay. That is the proportion of samples in this cut times the entropy of this cut. Again, this is 0.92 as I said earlier. Okay. Minus, we'll come to the other node now. Okay. This is the other node. Okay. So we'll see what is the proportion of samples in this cut. That is 2 by 5 times what is the entropy of this node. That is 0. Okay. Now we'll calculate this thing. This will come out to be 0.418. Okay. So this is the information gain that we are gaining by using this cut, this age parameter. Okay. So initially, without using this age parameter, our entropy would be 0.97. And with using this age parameter, our entropy will be this. Okay, the negative sign, this 3.5.92 and this whole thing. Now we are subtracting those two, and we are seeing what is the gain in information that we are getting by using this cut. So this will tell you how important this age parameter is in determining your y value. Okay. So this you can see, you can also visualize this as a percentage importance of the cut or the node. Okay. Fair enough. I think we are done with the calculation part. If you have any questions. After this, we will not do any calculation. This is the last calculation we do. Yeah, someone is saying entropy is lack of information. Yeah, in a sense, yeah, your system is so chaotic that you cannot keep track of the information. Right? Initially, you have like your system has total, all the ones and the zeros together, and at the end and the leaf nodes you see only zeros or ones. So you have like proper information that in this node you will have only zero values, in this node you have only one values. So yeah, so that is basically in that sense entropy is a lack of information.